Hello, 5th and 6th grade. We're going to go on to the next section of science today, which is star populations. We have a guest today. We are doing science with Sam, who wanted to join us for the lesson. So he's going to listen as well. All right, we are on page 144 in your science books titled Star Populations, and let's read some vocabulary first. Luminosity. The amount of light radiated into space per second by a star. Main sequence. A diagonal area on the HR diagram in which most stars are found. White dwarf. A small, very hot, very dense star. And giant. A large, bright star with low surface temperature. A person might expect to find an even distribution of all types of stars, regardless of size and magnitude. However, just as certain organisms on Earth are more abundant than others, certain types of stars are more abundant in the heavens than others. Scientists know this from the Hertzsprung-Russell or HR diagram, which two astronomers designed to chart the stars. They plotted the amount of light that the stars radiate compared to their temperature. On the right-hand side of the graph, each star's luminosity is compared to that of the sun. Luminosity is simply an amount of energy output. Absolute magnitude compares luminosity at a standard distance. The x-axis shows the Kelvin temperatures. The absolute magnitudes of a star are listed on the y-axis. So if you look at that chart below, you have an HR diagram. On the left-hand side, you have absolute magnitudes ranging from positive 15 to negative 10. Remember, the more negative the number, the larger and brighter the star is. On the bottom scale, you have the surface temperature in kelvins, which is a scale of temperature that exceeds Fahrenheit or Celsius that we use. And then on the right-hand side, you have luminosity, or how it compares to the brightness and magnitude of our own sun. So that goes from 1/100th of the brightness of our own sun up to 10,000 times the brightness of our sun. And then you have a bunch of clusters of stars throughout that chart. So, and they're circled by their categories. So you have white dwarfs at the bottom. You have the main sequence stars, you have giants, and then you have supergiants. By using the HR diagram, astronomers can estimate the size of stars. Since the size of a star is not directly observable, it must be inferred from collecting data. Placement on the HR diagram shows astronomers that most stars fall together in a diagonal pattern. This area is known as the main sequence. About 90% of all identified stars are main sequence stars, which are small to medium size. The sun, yellow in color and medium in size, is a main sequence star. If red represents hot and blue represents cold, why are hotter stars blue or white in color? Question for you. The HR diagram also reveals three other star populations. A white dwarf found in area A has a fairly high temperature but low absolute magnitude. This is because it is very small. A star plotted in the area B is the opposite of a white dwarf. It is relatively cool yet very bright. A cool star can burn brightly because of its great size. Each star in this population is known as a giant and is usually red in color. The population of stars found around area C has a greater variety of temperatures. The stars themselves are very large. They are known as supergiants and may be blue, yellow, or red. One of the largest known stars, Betelgeuse, is a reddish-orange supergiant. Sirius A, the brightest star in the night sky, is a main sequence star. It's the tiniest stellar companion, Sirius B, a white dwarf, can be seen in the lower left. Sirius A and B are 8.6 light years from the Earth. So you have that large Sirius A, and then you can see a little dot to the left of it, and that's Sirius B. So you can see comparison. It just shows the distance that they are apart based off their size that we can see. Betelgeuse in the constellation Orion is cooler, yet 1,000 times more massive than Earth's sun. If it were placed where Earth's sun is, it would extend beyond Jupiter's orbit. That's pretty amazing. In the field, the HR diagram used in astronomy is known as an XY scatter plot. This type of graph is used in research of all types and shows normal relationships between two characteristics. For example, doctors use XY scatter plots to establish normal patterns in child development. The chart displayed here of head sizes among infants. So we've been doing charts in math, and XY chart, remember, like with a line plot, is the X is on the bottom and the Y goes vertical. And so on the chart, you would go over X and then up Y, and then where those two meet is where you would put a dot. And then you would continue on with your data, and you would plot it with a line. And so what we use with this type of graph for the stars is you would plot where each star is, and then instead of connecting them all with lines, you're going to draw circles around them in order to show groupings of stars within the same category. Okay, we are going to be turning in your lab book. So go ahead and grab your lab book, and we're turning to 12.3. And we're actually going to be making one of these plot graphs together. So 12.3a, go ahead and grab that. Identifying stars is what we're looking at. Okay, and it says the following chart is a list of commonly studied stars. Their approximate surface temperatures are rounded to the nearest 1,000, and the absolute magnitudes are shown. Use this data to place the label. You can see the first column in the chart says label. Place the label letter for each star in the appropriate location on the HR diagram on the next science notebook page. The first two are already plotted as examples. Okay, so these are all names of actual stars that have been researched into what their approximate surface temperature is and what their absolute magnitude is. So we are going to plot these on a graph, just like we saw in the chapter that we were reading. All right. So on that chart, they did the first two for you. Okay. I'm just going to move you back a little bit. Okay, so on the side here of the chart, we have the absolute magnitude, so going from positive 15 to negative 10. On the bottom, we have the surface temperature going from 50,000 kelvins to 3,000 kelvins. On this side, we have the luminosity, so comparing it to our own sun. So we have 1/100th of our sun's magnitude up to 10,000 times our sun's luminosity. And then it's labeled on the top as our HR diagram. All right, we have A and B have already been plotted for us. So if we look back on the chart on 12.3a, the chart says Sirius A is what we are labeling as A, and the approximate surface temperature is 9,000 Kelvin. And so we're going to look down here at where 9,000 Kelvin would fall, and that's about somewhere between these 2 points. And then, so this is our x-axis, so over to about 9,000 Kelvin, and then the absolute magnitude is 1.4. And so we're going to be going up the side. We're going to look at our absolute magnitude on the side here, and it's going to be right below 0 because we're at 1.4. Where those two meet is where we're putting our plot for, and we're labeling it as A instead of Sirius A because we're not going to have enough space to put all of the names of all the stars on this plot graph. Okay, so we have A, they've done Sirius A, and they've also done Arcticus B, and we're going to go ahead and do the rest together. I'm going to prop the computer up a little higher so it's a little clearer for us to see. Okay, that's better. All right, so let's go through and do this together. If we look at C on our chart, C is Vega, the star Vega, and the approximate surface temperature, so looking on our x-axis first, is 10,000 degrees. So that's going to be right before the 11,000. So 10,000 degrees. And then the absolute magnitude is 0.6, positive 0.6. So that's going to fall right below 0. And so we're going to follow those two up. It's going to be a little higher than our A plot because A was 1.14. I'm actually going to move my A plot down a little bit. I think I made it a little too high. So we're going to put A here. Okay, and so when we follow these up, just about at 0, we're going to plot that about right here, and we're going to label that C. Okay, so yours should be somewhere right around 0 on absolute magnitude, and straight up from about 10,000 kelvins for the surface temperature. And then we're going to label it C. For D, star name Capella. Capella is 6,000 kelvins. So we're over here. We have 6,000. It has its own line, so we know exactly where we're going with there. So 6,000 kelvins, and we're going up to positive 0.4. So again, right below the 0. And so we're going to go straight up here, straight over, and we're going to put a dot there. And we are going to label that D. Okay, now this is a little bit of guesstimate work since it doesn't have a grid for you to do exact points on it. So just fill it about where about the two would meet and put a dot. All right, E, Rigel is the next star. So Rigel is 15,000 kelvins in surface temperature. And so that's going to be between the 11,000 and the 25,000. So 15,000 kelvins, and we're at negative 8.1. So we're going to be going way up to the top, almost to the 10. We're going to put a dot, and we're going to label that E. Okay, and that's for star name Rigel. For star F, we have Procyon A, and Procyon A is 7,000 kelvins, so right before 7,500. 7,000 kelvins, and we're at positive 2.6 magnitude. Okay, so if we're at positive 2.6 magnitude, we have positive 5 and positive 0 here, so it's going to be right in the middle. So we're going to come about right here. Okay, and we're going to label that F. Okay, great. So that is star F, Procyon A. G, Betelgeuse, we're at 3,000 Kelvin, so way over here, one of the cooler stars, 3,000 kelvins, and we're at negative 7.2. So although it's cooler, we are way up here in absolute magnitude. So that's going to tell us this is going to be a much larger star. So 3,000 kelvins, and we're going all the way up to negative 7.2, about here, and we're going to label that as G. Okay. I'm just going to turn my overhead light down a little bit so it doesn't have such a glare. There you go. Now you can see it. All right. The next one, we are on H, and we're on Altair, star named Altair. And Altair has a surface temperature of 8,000 kelvins, so right over past the 7.5, 8,000 kelvins, and we're at positive 2.3. So very close to where we were before, between A and F. So we're going to draw it about here, and we're going to label it H. Okay? It's okay that they're close together. All right, so that was star Altair. The next one, I, Aldebaran. So Aldebaran is 4,000 surface temperature in Kelvin. So 4,000 kelvins. So we're going to be way down here again. 4,000 kelvins. And we're at negative 0.3 absolute magnitude. So here's our 0. We're going to go up to negative 0.3. We're going to go over to 4,000 kelvins. And we're going to put our dot there. And we're going to label it I. J is next, and we have Spica, the star Spica. Spica is 22,000 approximate Kelvin for temperature. So 22,000, so we're way down here at the other end of the chart. 22,000 Kelvin, and we're at negative 3.2. So we're going to be following this all the way up to about here, negative 3.2, and we're going to label that as J. Next we have K, which is Pollux. And Pollux is 5,000 kelvins. So we're going back down here. We have 5,000 exactly on one of the lines. 5,000 kelvins. And its absolute magnitude is positive 0.7. So right before the 0, positive 0.7 and 5,000. So we're going to follow this up, and we're going to go about right here. And we're labeling this K. L, we have Deneb. The star Deneb is 9,000 kelvins, so about between 7,500 and 11,000. So 9,000 kelvins, and it's negative 7.2. So we're heading all the way up here to negative 7.2, right below where we had labeled E, and we're going to label that L. After L, we have Sirius B, which we're going to be labeling M. So Sirius B is 25,000 Kelvin in temperature. And then we're at positive 11.33 absolute magnitude. So we're way down here. So we're about right here at 11.33 absolute magnitude, and we're going to label that M. The next star that we'll be labeling N is Achernar. And Achernar is 14,000 kelvins, so about here, 14,000 kelvins, and negative 1.3 absolute magnitude. So we're heading up again right above the 0, negative 1.3, and we're going to be labeling that N. You can sort of start to see some patterns arising among the plots that we have. The next star that we're labeling O is Antares, and Antares is 4,000 Kelvin, and we're at negative 5.2. So here's negative 5, it's going to be right above it. Where those two meet, we're going to draw our dot, and we are going to label that O. Next we have P, and that's going to be for star Procyon B. And Procyon B is 8,000 kelvins. So about right here, 8,000 kelvins. And we are at positive 13.0. So right above where we're at. Positive 13.0. And we're going to label that P. And the last one we have is 40 Ari B. We're going to be labeling this Q. We are at 17,000 approximate temperature, so about here. And it's at positive 12 absolute magnitude. So we're going to put that about here, and we're going to label that Q. All right, so we have all of our stars on our graph. If we look at the directions on top of the page with the graph, on page 12.3b, it says, after plotting each star, identify the 4 populations of stars on the HR diagram by drawing a circle around each population. Then, determine the type of each star by comparing its location on the HR diagram to the information below. Write the correct identification for each star, white dwarf, main sequence, giant, or supergiant, in the type of star column on the chart of the previous science notebook page. So just some definitions again of what these different types of stars mean. A white dwarf is a very small star with fairly high temperatures and low absolute magnitude. Main sequence are small to medium-sized stars containing the majority of stars arranged along a diagonal line in the middle of the HR diagram. Giants are large-sized stars with fairly low temperatures at high absolute magnitude. And supergiants is the largest stars with low to medium temperatures and high absolute magnitude. So if we look at our groupings here, these down at the bottom with the high temperatures but low absolute magnitude, these are our white dwarfs. And we can circle those. Okay, so these are our white dwarfs. This line that cuts kind of through the middle here is our main sequence. So if you want to just write main sequence in this space here. And we're going to circle this diagonal group of stars. Main sequence. Over here, this grouping of 4 are our giants. So we can circle our giants. And then the rest of these at the top are the supergiants. So go ahead and label your sections. Circle those star clusters. So the bottom, high temperature, low absolute magnitude, so they don't look as bright, are our white dwarfs. The middle, we have our main sequence stars, which are medium, so they kind of fall in the middle of temperature versus brightness. Remember, the sun falls into this category. We have our giants, which are lower temperature but higher magnitude, which means they're brighter because they're larger and they have more energy to burn. And then at the top we have supergiants. Again, lowest temperature stars, highest magnitude because they're so large. They have a lot more energy to burn, so they burn brighter even though the temperature is lower. Okay, your job for the rest of this today is to look through these labels, go back to the chart on the chart before, and there's a column that says type of star. And so you're going to write what type of star it is for each one. Is it a supergiant, a giant, a main sequence, or a dwarf? And so, for instance, for A, one of the ones they already gave us, we're going to find A on our plot graph, which is here, and this is in the main sequence area. And so on your chart under type of star, you are going to write main sequence. Okay, B is the second one they did for you over here. We have grouped that in the giants star category, and so back on your chart, you're going to write giant in the column for type of star. Go ahead and do that for the rest of the stars, and then that will be all we have for today for chapter 12.3. Next time, we're going on to 12.4, which is star life cycles. How do stars begin? What happens over the course of their life? And what happens when their life comes to a close? We'll see you then.